Good morning, ladies and gentlemen. Let's take a look at the integrand expression in each of these three Bellwork questions. The key is deciding what strategy is going to be appropriate to use. So when we're dealing with a rational integrand function, we want to be thinking about the degree of the numerator versus the degree of the denominator. If the degree of the numerator is, 1 less than the degree of the denominator, right, we've got a potential for that acting as part of the derivative of the base, right? Part of the derivative of the denominator, and it could be a chain rule problem, right? So we could do like a power rule, we could do a natural log rule, something like that. However, if the degree of the numerator is greater than or equal to the degree of the denominator, typically we'll have to use the strategy of polynomial long division to rewrite, and then see if we recognize the integrand, or if it's rewritten in a form that we can integrate term by term. And then lastly, we may have to rewrite in fully factored form and use partial fraction decomposition to rewrite my rational expression as a sum of simpler fractions for which I do have rules. And so I tried to mix up things so that we can kind of get a different kind of practice from each of our Bellwork questions. All right, so let's go ahead and take a look at the first one. Notice how the rational expression in number 1, right, the numerator and denominator are connected, and they're separated by a degree of 1. And so what was the connection between those two? Emily?
Natural log.
Yeah, natural log ends up being our strategy because the numerator function, 2x plus 1, is the exact derivative of my denominator, x squared plus x minus 6. And so I could interpret this as a quantity on the bottom raised to the first power, whose derivative of the quantity, 2x plus 1, is present in the numerator. So I don't have to provide a constant, I don't have to cancel anything out, we're all set to go with a natural log rule, okay? So this is simply natural log of absolute value of x squared plus x minus 6. Those bars plus c. Raise your hand if you already have that. Right, that's a fast one, right? That's a fast one. Good job. I realize now that once I've begun the recording and have the USB plugged in that I can't play the sound for that. But when I save the recording at the end, then we'll go ahead and play it. So remind me at the end, okay? Don't worry, because it'll be a great setup for your practice worksheet that I just worked on yesterday afternoon to make. Oh yeah. All right, so what's up with number 2? Well, in number 2, the degree of the numerator is greater than or equal to the degree of the denominator. And so first, I'll use polynomial long division as a means to rewrite that rational expression. So how do we do that? I can't wait to share with you a video to remind us how to do that. But first thing we're going to do is take my top, x cubed plus x, and we're going to divide it by the bottom, x minus 1, to see how many times that x minus 1 goes into it. So what do? Well, we focus on the dominant. That is to say, x goes into x cubed how many times? X squared times. Now we'll do top times the side all the way through. So x squared times x is x cubed minus x squared. Next step, subtract. We'll go ahead and subtract. If we're doing it correctly, right, this term should drop out. So x cubed minus x cubed is 0x cubes. Let's keep track of our expressions here. It looks like we have opposite of negative x squared, means that we have positive x squared. And we also have this plus x here. All right, so we've got a positive x squared and we've got the positive x when we bring down. Everybody see that? Next dominant. X goes into x squared how many times? Well, it goes in x times, positive x times. So now top times the side all the way through. So x times x minus 1 is x squared minus x. Next step, subtract. So x squared minus x squared is no x squared. And then x minus a negative x is plus a positive x. I'm getting 2x. You guys get 2x here? Great. Now we'll go ahead and do it one more time. X dominant goes into 2x how many times? 2 times. Then I'll do top times the side all the way through. 2 times x minus 1 is 2x minus 2. I think this is the last go-go gadget arm. Subtract. And voila, there go the x's. Minus a negative 2 is plus a positive 2. So it looks to me that x cubed plus x divided by x minus 1 is x squared plus x plus 2 with a remainder of 2. Raise your hand if you got this polynomial long division result. You get that? Great. So who cares, right? Why was that useful? Well, now I can rewrite the integrand rational expression as x squared plus x plus 2, and then plus 2 over x minus 1. Right? I can rewrite that now as a sum or difference of individual terms, each of which I have a rule for. So I didn't have a rule for the original, but now I do have a rule. So let's go ahead and rewrite that. I'm going to get the integral of x squared plus x plus 2 plus 2 over x minus 1. And we can simply go term by term. Power rule, constant, and natural log. So x cubed over 3 plus x squared over 2 plus 2x plus 2 natural log absolute value of. I thought I was going to have to go to that term again, but we might have to.
Oh, no.
No! Natural log of absolute value of x minus 1, close bars, plus c. All right, the moment you've all been waiting for? No, Tyler, not that moment. Who got this? Everybody get all the way to the end for number 2? Hey, that's great news. So, we've recognized the derivative of the denominator function was present, so we just used straight up natural log and undid the chain rule. We used polynomial long division as a means to rewrite our rational expression, right, in a form that I recognize and went term by term. So what's up next? Well, now we get to do our new stuff. That is the derivative of the top here. I'm sorry, the derivative of the denominator function would be 2x plus 1. And I have 2x plus 16, right? And while I could break up that numerator as 2x over bottom plus 16 over bottom, then it still won't help me because the derivative of the denominator function still won't be present. And so I do have a sum of difference in the numerator, but breaking up is still not going to help. So what can I do? Well, I can try factoring the denominator and write in my f cubed, fully factored form. All right, let's go ahead and try a partial decomposition here. So we'll go ahead and rewrite this as the integral of 2x plus 16. And we could factor that, but I'll just leave it. I think it's going to be fine. And we'll rewrite the denominator in fully factored form. Go ahead and tell the class what the denominator factors to when I call on you. Our resident expert factor, Danny?
X plus 3, x minus 2.
X plus 3 and x minus 2. Thank you. So we've got our minus 2x plus 3x plus 1x minus 6. Good job. Now, I'm going to rewrite this fraction as a sum or difference of individual simpler fractions in a technique called partial fraction decomposition. In fact, we're guaranteed to be able to do this. Now that we've factored our denominator, we're guaranteed to be able to do this. We just have to find what numerators, a and b, right, must exist in order to produce that 2x plus 16 when simplified. So I'll go ahead and now go to my bracket. What? Well, I'm going to do my little aside, and I'm going to set up my partial fraction decomposition. I know that some value a over x plus 3 plus some value b over x minus 2 must combine to give me the original 2x plus 16 all over x plus 3 times x minus 2. In order to combine those two fractions through addition or subtraction, what would we need to create? A common denominator. And so the first term would require multiplication by quantity x minus 2 over x minus 2. The second fraction would require multiplication by quantity x plus 3 over x plus 3. And that would equal this end result. Because we've seen how this goes, we're going to forget about the denominators and use the factors and equate that to the numerator to see what happens. In other words, a times x minus 2 plus b times x plus 3 has to equal 2x plus 16 when combining my terms in order to simplify to the original. So what will we do? Well, we'll figure out the values of a and b by a purposeful selection values of x. What would you like to choose x to be so that we can easily find the value of a or b? Tyler? 2, I'm down. However, that's not going to be PDFable. So we'll fix that right now. So if we choose x to be 2, then the first term drops out, and we're left with 2 plus 3 is 5b equals 2 times 2 is 4 plus 16 is 20. Yes, 20. Which means that b equals 4. Hey, that's not so bad. What else should we choose x to be? Courtney?
-3.
I'm down. Let's let x equal -3. Then that will force the second b term to drop out, and I'm left with -3 minus 2 is -5a equals 2 times -3 is -6 plus 16 is -10. No, positive 10. Positive 10? So I find that a equals -2. Raise your hand if you had these values for a and b. Did you get those? Yes? Yes? Great. So what do we do? Now we're ready to close our brackets. We figured out the partial fraction decomposition of the original, and now we can rewrite my original as -2 over x plus 3 plus 4 over x minus 2, and integrate term by term using natural log. That's powerful. So we didn't have a rule in the original, and now we do. That's pretty cool, and a new technique, so I'm excited about that. All right, let's rewrite the original then. We want the integral of -2 over x plus 3 plus 4 over x minus 2 with respect to x, and that's a one-stepper in each case. So I get the opposite of 2 natural log of absolute value x plus 3 close bars plus 4 natural log of absolute value x minus 2 close bars plus c, and we can box at that point. Now in the back of the Finney Demand awaits Kennedy Rasood text, it's going to kick these coefficients up on top as exponents and then condense the logs in accordance with the quotient property or the sum or difference right here of logs into a single log as an expression, but either way it's fine with me. All right, so raise your hand if you got all the way to the end of 3. Anybody get all the way to the end? Hey, that's great news. Okay, good job. So that's our brand new stuff. What questions do you have about today's Bellwork? We're going to take just a minute here and then pause it and get our OTL number 6 check taken care of. So I included number 1 and number 2 in our note sheet. They were already in your previous, and so you won't see them here because these are in last class. However, this is if we wanted extra practice with our partial fraction decomposition. So what I want you to do is go ahead and take a look at number 1. This was the number 6 that allowed our kickoff, to the partial fraction party. And number 2 was towards the end of our day 6 notes that we didn't get a chance to complete as we ran out of time. What we're going to do is a quick poll the class to see if we'd like to do another partial fraction decomposition or if we'd like to get to our integration practice. No pressure, No pressure. Everybody, we're going to go ahead and now, we've got 2 votes coming up. So we want to complete number 1 together. Raise your hand. I want to complete number 1 together. Don't get down. That's 2, okay? No problem. And number 2, I want to complete number 2 together. Nobody wants to do number 2? Nobody wants to. You guys want to practice. And that's fine with me. I included these. They're already in your day 6 note sheet. Okay, I just included them in today's in case you wanted to discuss it because the technique is newer. Okay. All right. So what I want you to do, you don't have to evaluate these. What I want you to do is go ahead and determine the overall strategy that will be employed in each of these problems with your partner and be ready to share with the whole class. And so you don't have to evaluate and go to the end. I just want to know what would be the rule or the strategy based on what this looks like. Okay, ladies and gentlemen, at this time I ask that you and your partner share the strategy, kind of for the first step or the approach, or the rule that would be used in each case. And so first let's just look at number 1. So what would the overall strategy be if you were to integrate number 1? Kobe and Sophia? Inverse tangent, raise your hand if you said this would be an inverse tangent rule for the antiderivative. That's correct. So this would be an inverse tangent rule. Right? This would be an inverse tangent rule for the first one. We have to do a little bit of work, right? We have to do a little bit of work to determine what constant was required, what the angle would be, but definitely the strategy would be to rewrite as 1 plus quantity squared for inverse tangent. All right, number 2. What overall strategy would be employed for number 2 then? Grace and Riley?
Partial fractions.
Yeah, number 2 is a partial fraction decomposition. This is not an x squared plus, right? It's x squared minus, so I could factor it as x plus 2, x minus 2, constant on top, right? So I'd go with partial fraction decomposition here. So partial fractions for short. And raise your hand again, same as Grace and Riley. Partial fractions for number 2, partial fractions, yes? Great. And lastly, number 3, what overall rule, technique, or strategy would we employ to start number 3? So what did you guys have for that, Courtney and Marissa?
Polynomial long division.
Polynomial long division, raise your hand if that's what you said. Polynomial long division is your first start, good? So polynomial long division, which may or may not result in still having to employ partial fractions, or it could end up being a summer difference for which we already have rules and we could get away with not having to do partial fractions, and we've seen each case in class in the past. Awesome. What questions do you guys have about our discussion today? So a shorter day, we're going to go ahead and take this opportunity to practice some of the new techniques we've learned. I want you to know that I've mixed up. I spent yesterday afternoon making this practice with integrals, but I would encourage you to do bookwork first so you don't, right? So that you're done with that. This is specific to our new technique of partial fractions. The practice with integrals, you guys, I mixed up different strategies and techniques. I also completed a key and just scanned it in. And so I still have to upload the answer key to Moodle, but you will be able to use your smartphone or electronic device during this class period to check. I just have to load it. However, first we need to check out a great polynomial long division video, right? So that you can basically know what it is, okay? You need to know what it is. And in order to do that, I need to save the recording so that I can unplug the USB and we can get our sound back. And so I'm going to go ahead and stop now the recording and save it, and then we'll rejoin to hear the video.